So in this part of video, we are gonna cover part C, that is data processing for feedback analytics. So we'll start with the ninth question that says student faculty feedback data may suffer from issues like accuracy, completeness, and consistency. Discuss each issue in this contents. Missing survey responses, example missing survey responses, contradictory ratings, purpose two other dimensions of data quality relevant to learning analytics. Now we will discuss the issues and their discussion in the feedback content. So the first issue is accuracy. So accuracy, the rating may be in this the rating may be incorrect or untruthful. Example: a student accidentally selects 1 instead of 10, or they intentionally give very low scores due to a personal variance, making the rating value inaccurate. Then the second issue is completeness. So in this, the data is missing certain values. Example: a student leaves the infrastructure section blank or skips optional text comments. Then third issue is consistency. In this, the data values conflict across different sources or within the same record. Example: a student rates the teaching quality highly, but provides a text comment saying the lecture were confusing and unhelpful. Now, the two other dimensions of data quality relevant to to learning analytics are: first is timeliness and second is believability. So, data must be available when it is needed. Example: feedback submitted immediately after a course module is more valuable for real-time intervention than feedback collected 6 months later. And believability is the data source must be reliable. Example: feedback collected anonymously via secure portal is more credible than comments gathered informally via social media poll. Now moving on to the 10th question that says discuss approaches such as ignoring tuples, filling manually, filling with constants, mean median mode imputation, class specific imputation, or most probable values methods. So in this, the first method is ignoring tuples. So its description is discard records with any missing values. Pros are simple and maintains data integrity. Cons are can lead to a massive loss of data, especially if records have sporadic missing values. Then the second method is filling manually. The description is requires domain expert input to replace missing values. Pros are highest potential accuracy. Cons are impractical and time consuming for large data sets. Then the third is filling with a constant. Though, so the description is replace missing values with a global constant. Pros are quick and easy, and cons are introduces bias and may distort statistical measure like the mean or mode. Then the fourth method is mean, median, mode, and imputation. So its description is replace missing numeric values with the mean or median, or missing categorical value with the mode. Pros are simple and preserves the mean. Cons are reduces variance, can distort distribution, and ignores relationship between attributes. Then the fifth method is class specific imputation. So its description is impute missing values based on the mean, median, mode of the record belonging to the same class. Pros are more accurate than global imputation as it leverages class information, and cons are requires label data and is complex for multi-class problems. Then the last is most probable value method. Its description is use sophisticated techniques like regression, decision tree induction, or Bayesian methods to predict the missing value based on other attribute values in the record. And its pros are most accurate imputation, maintains data correlation, and cons are high computational cost and complexity. Moving on to the 11th question, that is consider the feedback rating, that is from 13 to 70, and A part is smooth the ratings using bin means with bin depth 3 and then illustrate steps. The second is suggest ways to detect outliers. Example: abnormally high or low satisfaction, and the C is discuss other methods for data smoothing. So first is smooth the rating using bin means, that is bin depth 3. So partitions into bins, that is depth 3. So group the sorted data into bins, each containing 3 values. So bin 1, 3. We will like this create the bins. So there will be 8 bins, each containing 3 values. Then the second is compute bin means. So we will compute the mean of all the bins. So we will get these values in this smoothed ratings as 14.67 to 35.00. Now the B part is suggest way to detect outliers. So the outliers are data points significantly different from others. So in this, the first is box plot analysis, which is IQR method. So calculate the in quartile range, that is IQR, which is equal to Q3 minus Q1. So we will calculate this. Then define outliers as points falling below, which is calculated by Q1 minus 1.5 into IQR, or above, which uses Q3 plus 1.5 into IQR. Then the upper bound, then the measurement of upper bound is 59. So any rating greater than 59 is a potential outlier. Then second we use Z-square method, which calculate the Z-score for each data point by the formula Z equals to X minus X bar upon sigma. Then the data points with a Z-score typically greater than 3 or less than equal to minus 3 are considered outliers. Then the third is visual inspection. Plot the data to visually identify isolated data points. Then the C part is discuss other methods for data smoothing. So first is bin boundary smoothing. Instead of using the mean, replace all values in a bin with the nearest bin boundary. Then the second is regression. So smooth the data by fitting it to a mathematical function. Values are replaced by the predicted value from the regression line. This is efficient if data is correlated. The third is moving average or windowing. So particularly useful for time series data, replace a data point with the average of its neighbor. Example, the average of previous two and the next two data points. Now moving on to the question 12, that is in data integration for AMC or MTech analytics. Discuss schema integration, handling redundant data. Example, duplicate entries from multiple surveys and resolving conflicts in values. So the challenge is ensuring attributes from different sources are mapped correctly. Example, one survey might call an attribute that is faculty score while another calls it teaching effectiveness. The solution is use metadata and data dictionaries to harmonize schemas, identify entity identification problems, then handling redundant data. So duplicate entries occur when the same student or rating is captured by multiple systems or service. So it is managed by correlation analysis to detect redundancy. If attributes are strongly correlated, one might be redundant and can be removed. Use data cleaning tools to identify and merge duplicate records based on primary key. Then resolving conflicts in values. So the same entity has different values for the same attribute across sources. Example, a student S has CGPA of 8.5 in the departmental record and CGPA of 8.2 in the central university record. So firstly, we will specify priority, use the values from the most reliable source. Then weighted averaging, compute a weighted average if sources have different quality ratings. Then consensus, that is for conflicting nominal data, use the majority vote or the most recent value. Then the 13th question is discuss normalization methods, that is first min max normalization, z-score normalization. C is z-score normalization using MAD, that is mean absolute deviation, and the D is decimal scaling. So the normalization scale attribute values to fall within a small specified range. So first is min max normalization 0 to 1 range. That is V dash is equals to V minus min of A upon max of A minus min of A. So it uses maps data to a specific range, typically from 0 to 1. It preserves the relationship among the original data values. Its limitations include highly sensitive to outliers as they determine the min and max and compress the range for the remaining data. Then the B is z-score normalization. So z-score normalization is calculated by V dash, that is V minus x bar upon sigma. So it transforms data to have a mean, that is x bar of 0, and a standard deviation of sigma, that is 1. This is useful for algorithms that assume a normal distribution, example clustering and classification. Then the limitations include the minimum and maximum values are not bounded. The presence of extreme outliers can still distort the mean and standard deviation. The C is z-score normalization using mean absolute deviation, that is MAD. So V dash is equals to V minus x upon MAD. Then it is similar to standard z-score but uses MAD instead of standard deviation. Its benefits include that MAD is less susceptible to outliers than sigma, making this version more robust when the data has extreme values. The D is decimal scaling. So it is calculated by V dash is equals to V upon 10 to the power j, where j is the smallest integer such that max of V dash is less than 1. So it normalizes the data by simply moving the data decimal point. Values fall into a range of -1 to 1. Its benefits include extremely simple and fast. No min and max bar or sigma needs to be calculated. Then the 14th is normalize the following faculty workload values, that is hours per semester. And it is given, the data is given as 200, 300, 400, 600 and 1000, and we need to calculate the normalization. Then the data is given as 200, 300, 400, 600 and 1000, where n is equals to 5, min is equals to 200 and max is equals to 1000. So we will calculate the sigma of V, which is 2500. Then the mean is calculated by 2500 by 5, that is 500. Sigma comes out to be 316.23. And the standard deviation of MAD, that is mean absolute deviation, which comes out to be 240. Now we will put all these values in this. So we will calculate first min max normalization. So its formula is V dash is equals to V minus min upon max minus min. So we will put the V as 200, 300, 400, 600 and 1000 and calculate these values. In the B part, we need to calculate z-score normalization. So its formula include V dash is equals to V minus 500 upon standard deviation, that is 316 by 316.23. We will put the V as 200, 300, 400, 600 and 1000 and we will calculate the values in the same way. Then the C part is z square using mean absolute deviation. In this, in place of sigma, we will use mean absolute deviation, that is 240. And in place of V, we will put these values and will calculate the z-score. Then decimal scaling. So we will use the formula of max of V. Then we will put the V as this and will calculate the values. Now moving on to the question 15. So the question 15 says, using the feedback ratings dataset, normalize the value 35 using min-max normalization 0 to 1 range, then z-score normalization, that is sigma, then decimal scaling, and the D part is discuss which method is more appropriate and why. So the feedback data has minimum of 30, maximum of the maximum of 70, x bar is equals to 28.0. The prompt gives sigma 12.94. So the A part is min max normalization. We will calculate it. So V dash becomes approximately equal to 0.386, and the B part is Z square normalization in which sigma is equals to 12.94. So V dash becomes 0.541. Then the decimal scaling becomes V dash is equals to 0.35. Then the D part is most approximate appropriate method. So it is the Z-score normalization, which is the B part. So the reason is machine learning algorithms often perform best when data follows a standard distribution with zero mean and unit variance. Z-score achieves this efficiently, removing scale bias and allowing for meaningful comparison of relative scores. Min-max is too sensitive to the outlier value of 70, and decimal scaling doesn't change the distribution shape or center it around 0. Now we will solve the other parts in the next part of the video.